The following podcast is a proud member of the Blue Collar Roots Network. Find all the shows by visiting bluecollarroots.com. And now, the man who takes the BS out of BS, Bill Spohn.
Welcome back to the Building HVAC Science podcast. As noted before, our passion here is to communicate with technicians and contractors in the field, those involved in HVAC and building performance, some information that's going to help them do their jobs better, make their lives easier. We'd like to create a better, more knowledgeable field of technicians. If you like what you heard today and you've not subscribed to the podcast, please consider doing so by typing Building HVAC Science into the search bar of one of those three typical services, Apple, the podcast app, or for Android, Google Play, Music, or Stitcher. You can also listen in your browser at bluecollarroots.com/Building HVAC Science, and shortly we'll have a YouTube channel up if that's your preferred way to listen. In this episode, I'll be talking about part 2 of my concepts on airflow measurements. And again, this is from a series of articles that I'm writing for Today's AC publication. That's a publication out of Florida. You can find that publication at www.todays-ac.com. For the quote of the day, I'm going to leave you with one that I believe is attributed to the Navy SEALs. There are two ways of doing things, the right way and, again, get it right. And now, on to the podcast. To recap, the last time we were here, I listed 4 main applications for airflow measurements. That's system, supply, return, and mechanical ventilation. I then drilled down into airflow measurements and covered the first bulk measurement, the temperature rise method. Now, in order to efficiently discuss the remaining methods, I'll group these according to some common factors that build upon each other and examine the assumptions, challenges, measuring ranges, and costs, amongst other things that we'll cover. Each common mode of airflow measurement, at its core, involves what I call a basic measurement. The basic measurements are temperature, pressure, electrical, airspeed, and time. Time. How does that factor in? Okay, just wait and see. We'll cover that. Last time, we covered the core measurement of temperature in the discussion of temperature rise method, which measures the change in air temperature due to a known input of thermal energy. To use the simplest formula, a key assumption is that the air is at a standard density. The conditions for standard air density are 68 degrees Fahrenheit, 0% relative humidity, and sea level altitude. That yields an air density of 0.075 pounds per cubic foot. I'm a real stickler. I put that 0 in front of the decimal every time. Just ask Jim Bergman. I used to annoy him with that constantly. As covered before, some of the temperature rise challenges include getting a good value for the input thermal energy, BTUHs, reading only the temperature of the air and nothing else. That means you have to be out of the line of sight of any other hot surfaces. You don't want to pick up that radiant energy. You also assure that no air is bypassing your measurement and you're measuring the bulk of air, all the air that's moving through the system. The measuring range on this is pretty unlimited, but the resolution and accuracy will be impacted by the exactness of your BTUH measurement and if you correct for air density. It can take up to 20 minutes or more to run this test, and the result you'll get is CFM, cubic feet per minute. Now, this is a good ballpark measurement if done with the proper technique. Next is the core measurement of pressure, which factors into 6 different airflow tests by my reckoning. The method of pressure measurement will also dictate your meter type. The static pressure test measures the change in static air pressure over a known restriction to correlate with a factory-measured airflow. Now, that's usually the restriction caused by a coil or heat exchanger, or perhaps the two of them in combination. A critical assumption is that you're using the proper chart of CFM versus static pressure for the specific equipment you're testing. You also need a manometer with sufficient accuracy to get the necessary readouts. A manometer, or a pressure gauge, with a resolution of 1/100th of an inch of water column is a good choice here. Now, some challenges presented by this method include having the restriction that you're testing, that's the coil or heat exchanger, in the same condition that it was in the factory. That is wet or dry, dirty or clean. I guess you would assume in a factory it would be a clean coil, for example, or a clean heat exchanger, not with years of use on it. And you would also have to look and see if the chart says it's a wet coil or a dirty coil if you're testing over an AC coil. You will also have to test exactly the same restrictions. Now, only those specified components that are in your specific chart is when it was profiled in the factory to develop its chart, and you must also use good test techniques. A measuring range really doesn't apply here, as you're matching a profile from the equipment manufacturer, and this method does not work outside of the single application. The resolution here can vary from 20 to 70 CFM per tenth of an inch of water column, and I get those numbers by looking at typical charts of static pressure change versus CFM. So these can be pretty big hops in the CFM chart. If you need a more accurate number, you'll need a more accurate manometer. Some of the tried and true digital manometers around the $100 to $200 price point yield an accuracy of plus or minus 0.08 inches of water column. Now, looking at those past steps, those big hops you could take, that means your measurements could be off by plus or minus 500 CFM or more. Now, that's just simply 8 of those hundredths of an inch times 70 CFM per hop on the chart. So that's 560 CFM. So recognize what you're getting into when you use this type of measurement. You're not going to get really superior accuracy. You'll need to include the test time to drill and plug the access holes. And you also need to use that equipment, a drill, some kind of step bit perhaps, and have some hole plugs. This test time can be around 15 minutes. And at the end of your test, your resulting measurement is CFM. Nice. Another use of pressure measurement comes in the form of a Duct blaster, which is a trademark of the Energy Conservatory. And they have a test method actually described in their instruction manual called the Duct Blaster Pressure Matching Method. You can do this with any form of duct pressure testing equipment, but they have the specific method spelled out in their instruction manual. The process here involves matching the normal system operating pressure of the air handler by using this externally connected duct leakage tester, which is basically a variable speed fan with a flow sensor integrated into the fan head. So this integrated measuring device gives you the CFM flow and a calibrated device as it moves the air by the fan that's inside it. So breaking this down, a duct blaster is a device typically used for measuring air leakage in ducts. There are a couple brands in the market, Retrotech and the Energy Conservatory, and you'll also hear of it in terms of being called a duct tester. Prices for this setup are around the $2,300 range at this point. Now that's pretty steep, but you got to remember, like a lot of things, accuracy has its price. This method, this kind of equipment will deliver superior accuracy, and it's sort of a one-shot deal. You hook it up correctly, you make the measurement, and there's your number. The airflow in this device is measured by creating a slightly negative pressure, or a vacuum, created over 3 tiny holes in a stainless steel tube, a thin tube that's formed into a ring that encircles the leading edge of the fan motor housing inside the duct blaster or duct leakage tester. So that's the way these things work. They have basically a circular Pitot tube, if you will. These units are well designed and precision calibrated. They require the use of a special 2-channel digital manometer that is purpose-built for a wide range of tests. An important assumption here is that you set up the test to minimize other pressure interferences in the system, in the house. For example, you want to turn off the air handler fan and open a window or a door between the building and the outside to prevent any pressure changes on the structure from upsetting the test steps. If the air handler fan is installed in an unconditioned space, unconditioned zone like a crawl space or an attic, you want to open any vents or access doors that connect that zone to the outside or to the rest of the building. Again, you're trying to minimize any pressure changes in that zone that are going to affect this fine resolution manometer you're using to test. Also, you want to make sure all supply and return registers are open and uncovered. And so if you're doing a duct leakage test, you usually tape up the supplies and returns to test the holding pressure. You want to make sure they've been untaped at this point if you did that test. System air filters should be replaced if they're dirty, or if you want to get a as-found type measurement, leave those dirty filters in place, and you'll get an airflow that includes the restriction of those air filters. This test can be performed at the air handler cabinet by fashioning a custom cabinet interface so that the duct tester's hose can be attached. Now that custom cabinet interface usually ends up getting made out of cardboard or wood, or if you're doing repetitive work where you have multiple units that are in the same configuration, you can actually build one out of wood or some other material. This testing can also be done if there's one central return. The variable speed fan limits the test range to about 1500 CFM, so this is generally not suitable for air conditioning systems that are 4 tons of cooling or greater. This method has been tested to an accuracy of plus or minus 3% when used with an appropriate high-resolution 2-channel digital manometer. The total test time here can approach the better part of an hour because of your potential need to fashion a custom interface to the air handler cabinet housing and to make sure that your house/pressure interferences are all set up properly. Yet the resultant measure is a CFM number with a very high accuracy, so it may be worthwhile to do. Did you know that Bacharach has been a leader in the design and manufacturing of combustion analysis equipment since 1909? Actually, I knew that fact because I used to work there for 10 years. What a great company. During their fall promotion, you can save on the purchase of a new combustion analyzer with rebates worth up to $350. That offer includes a free 2-year subscription for their exclusive B-Smart Sensor Exchange program with the purchase of a Firite InTech or Insight Plus. With the B-Smart Sensor Exchange program, pre-calibrated sensors are shipped directly to you. No more hassle, no more downtime when you return your analyzer to the factory for calibration. Download your rebate form today at mybacharach.com/offers. That's mybacharach.com/offers. And enter the promo code HVAC Science. That's HVAC SCIENCE. That will let them know that you heard about it here on the Building HVAC Science podcast. This is a time-limited offer, so be sure to do it today. Let's continue on now with other types of airflow measurements that use pressure measurements at their core, or as I call the basic measurement, pressure. The Pitot Tube test involves using a small kit. You need a Pitot Tube, and we'll talk about what that is in a minute, a manometer with the proper range, and a couple of hoses to connect that Pitot Tube to the manometer. Now, kits can be had for $200 and up. However, if you want to read lower velocities, you'll need a finer resolution manometer, which could cost you more like $500 and up per kit. Now, the Pitot Tube itself was invented in the early 1700s by the French physicist Henri Pitot. He was French, therefore the pronunciation is Pitot, not Pitot, even though it's spelled P-I-T-O-T. Another French scientist named Henry Darcy redeveloped it into its modern form, which is a tube within a tube instead of 2 separate tubes. And he did this in the mid-1800s. A true Pitot tube only measures one pressure, the total or stagnation pressure of a fluid flowing. Now, air is a fluid. Keep that in mind as we talk about this going forward. Today, we actually use a Pitot static probe, which combines the static and total pressure. However, we're generally a little lazy nowadays, and we just call them Pitot tubes, when technically they're Pitot static tubes. Pitot static's a great name because it reminds you, as it embodies what's going on in this device. The Pitot pressure, or total pressure, is measured by the open hole at the tip of the probe, while static pressure is measured by the tiny holes in the side of the tip of the probe. Think back to what we just mentioned a few minutes ago, that little ring with the tiny holes in it on the duct blaster or duct leakage tester. The same type of measurements going on here as it was there. Now, maybe a fun fact for you. Pitot tubes are actually used to determine the velocity of airplanes. Due to the critical nature of always needing to know a plane's airspeed, that's pretty important here, coupled with the varying environmental conditions outside of a plane, these Pitot tubes are often heated so they don't clog due to becoming iced over with changing weather and humidity conditions, water conditions. So don't mistake a Pitot tube for a handle to grab on when you're getting around a plane, or you might get burnt. Literally, I came real close one time. Okay, going back. When you subtract the static pressure in this Pitot static tube from the total pressure, you're left with something called the dynamic pressure, or the pressure due to the air velocity, which we call typically the velocity pressure. The modern Pitot tube is elegantly engineered to marry one tube inside the other, so the two pressure measurements are pretty easily carried out in the same place at the same time. And the ports connect your hoses are within inches of each other for you to hook up your hoses to go back to the manometer. Now we'll talk about an equation. It's called the Bernoulli Equation. You might have heard that before. I see it slung around a lot on Facebook and other places, other forums. The Bernoulli Equation is used to move from velocity pressure measurements to the actual velocity. Now, this equation involves the density of the air. So as we discussed before at other times, air density changes with temperature, humidity, and barometric pressure. So it's important to know, as this is going to affect the velocity number that comes out of your calculation, out of your equation. Now, luckily, some digital pressure meters allow for air density adjustment, but if you're not able to adjust for density, you could already be building in an error of around 10% or more. So just keep that in mind. Additionally, since the Bernoulli equation has the pressure measurement being buried inside a square root, you cannot get an average velocity from taking multiple pressure measurements and averaging them together. Now, I know this because I made the mistake many years ago and was wondering, what the heck is wrong with my calculation here? Well, it's the fact that you have to take separate pressure measurements, calculate the velocity, then and only then can you average them together. Fortunately, there are digital manometers that actually report the velocity directly, and even some that will time average or point average the velocity for you. So your number's built up inside this digital meter, another case for digital meters here. Now, the Pitot Tube only measures a very small region that's in the diameter of the probe tip. The probe itself knows nothing about the air velocity, even a fraction of an inch away from the probe itself. So the probe placement is critical. It's also necessary to realize air velocity is turbulent, and you're usually measuring in a duct system with a Pitot tube. This air velocity is turbulent and varies greatly across the duct or at the supply or return. This variation in velocity can be so difficult to capture at supplies and returns, I generally don't recommend Pitot tubes be used at supplies and returns. Even if we have smooth flow or laminar flow, as opposed to turbulent flow, the variation present due to the drag of the air on the walls of the duct will force you to move the probe around in the duct to develop what this pattern of velocity is. Now, this type of movement across the duct through the duct is called a traverse. Now, we're not going to dig too far into these details, but suffice to say, there are well-tested ways of doing repeatable traverses. The most popular method is called the log-Chebyshev method. Some digital meters now come with apps that actually guide you through the measurement locations in a traverse, sort of minimizing the amount of research you have to do. The meter will actually tell you where to go to put the probe to make that measurement. The best place to use a Pitot tube is where the airflow is smooth or laminar, as we mentioned before, so the best place to measure is at least 7.5 duct diameters downstream and at least 3 duct diameters upstream from any changes in the air's path. And so those changes might be turns, obstructions, reductions, or expansions in the ductwork. Now, this kind of advice comes from ASHRAE, the American Society of Heating, Refrigeration, and Air Conditioning Engineers, as part of one of their standards where they give you advice on how to do these kind of tests. You can do a traverse in as little as 2 duct diameters downstream and 1 duct diameter upstream from a disruption or a duct ruption, duct disruption, but your measurement accuracy is going to suffer because of that potential variation in the airflow across the traverse of the duct. Now, upstream disruptions also affect airflow. You'll notice we mentioned up and downstream in the last couple minutes here, because the air is going to slow down like a traffic jam and cause a pressure wave to come back upstream, changing the velocity, slowing the velocity in the opposite direction. So that air is really tricky. As I said before in another session, air is squishy. It's really a hard thing to try to measure. Pitot tubes can give you velocity measurements, but then you need to translate it into CFM, cubic feet per minute. And you do that by multiplying the cross-sectional area of your measurement location, where you're taking the measurement, by the average velocity. Accurate cross-sectional measurements are vital to getting good CFM results. So the basic stuff of measuring area is very critical here too. Now, while I have nothing against analog pressure meters, that is diaphragm type, dial type, slack tube, or incline manometers, all they give you is a pressure. It's standard conditions of the air. You're going to need to correct for density, do the Bernoulli equation math to get the velocity, Then average a chain of these velocity results by hand and then multiply by the cross-sectional area. Many digital pressure meters do all that for you in real time and allow you to chart the results or email or share them electronically. So again, the case for electronic or digital measurements here comes strikingly forward. So take a look at your cost versus time, the chance for error or delay from taking a reading to knowing the results, and you're going to likely choose digital. For lower air velocity speeds, that is, in fact, most residential applications, you're going to need a fine resolution pressure gauge. That means a resolution with about 1/1000th of an inch of water column, or 1/10 of a Pascal. If you use your typical 1/100th of an inch resolution manometer, which you also use for gas pressure checking, filter drop, total external static pressure measurements, you're not going to get good pitot readings from it much below 700 feet per minute. So this is usually not suitable for most residential ducts because 700 feet per minute is usually an area where you start to get noise from the duct and you're already tuning things down. There's some new Bluetooth, which means they're app-connected digital manometers out there with great pricing that have all the right ranges, averaging, calculations, density corrections, all built in. Now, the time to do one of these tests can take up to about 10 minutes if you have previously drilled the access holes and then also come back and plug them. A few minutes longer if this is your first time. So hopefully these couple of examples illustrated here about doing pressure-related air velocity measurements and airflow measurements are a little bit illuminating to you, and you'll come back again and listen for more on the Building HVAC Science podcast. Again, thank you for listening. I hope you grabbed a few more tidbits of information as I covered part 2 of my airflow wisdom. Now, if you want to keep on other things that I find interesting, you want to follow us on Facebook by typing Building HVAC Science into the Facebook search bar. If you're interested in becoming a sponsor of the Building HVAC Science podcast, please email me at bill@bluecollarroots.com. Little disclaimer here, some of the topics that we discuss in this podcast may require technical training for proper interpretations or safe execution. Now, if you're a trained pro, then you can go right ahead. If you're not, please consult with and hire a trained pro. Also, if you're in the market for some of the tools or test instruments we mentioned in our podcast, please take a look at what TruTech Tools have to offer. www.trutechtools.com. You can use the code HVACBS for a nice discount. And in full disclosure, I'm the BS, the Bill Spohn, that's a co-owner of TruTech. So the code is HVACBS. That kind of says it all right there. As you know, we appreciate you listening and following us on the Building HVAC Science podcast. If you have not subscribed, please consider doing so. Clicking subscribe will help keep you up to date on what's happening in the world of building HVAC science, and it's going to really help out our ratings for Google, iTunes, etc. If you also want to go to that page and give us some ideas for future episodes, we'd be happy to do so. We've got a lot of guests coming up in the next few episodes. We hope you're going to enjoy it. Thanks again. Have a great day.